Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you at my T.Y.B.Sc Analytical Chemistry class. I am Dr.S.R.Labhade, working as Associate Professor in the Department of Chemistry at T.Y.B.Sc College, Nashik. Student, in today's lecture we discuss the technique of atomic spectroscopy. Student, in previous lecture we discussed theory, principle, working, instrumentation and applications of molecular absorption spectroscopy. And we also discussed the different terminology related with molecular absorption spectroscopy. In today's lecture we discuss the technique of atomic spectroscopy, that is called as flame emission spectroscopy. Flame emission spectroscopy, also called as atomic emission spectroscopy. This technique involves the measurement of radiant power at specific wavelength, and therefore it is also called as a flame photometry. Flame atomic emission spectroscopy, that is a technique of spectroscopy concerned with the measurement of atomic species. In last lecture we discussed the spectroscopy. We know that spectroscopy is a branch of science that deals with the qualitative and quantitative analysis of molecular and atomic species via their interaction with electromagnetic radiation. Therefore, interaction of electromagnetic radiation with matter, that tells us what is the material and how much it is. That means spectroscopy is the most important tool of identification and estimation of atomic and molecular species. Therefore, based on the measurement or application of the spectroscopy, it is also called as a molecular spectroscopy, and second one is called as atomic spectroscopy. In molecular spectroscopy, we measure the concentration or amount of molecular species present in the solution. When that molecular species absorbs electromagnetic radiation, then it is absorption molecular spectroscopy, and when it is related with measurement of emission of molecular species, then it is called as molecular emission spectroscopy. Similarly, in atomic spectroscopy, when atom absorbs electromagnetic radiation, then it is called as atomic absorption spectroscopy. And when we measure the emission of emission of the atomic species, then it is called as atomic emission spectroscopy. Therefore, spectroscopy based on the measurement of the type of material classify as a molecular spectroscopy and atomic spectroscopy. If measurement mode is absorption, then it is molecular absorption spectroscopy. Measurement mode is emission, then it is molecular emission spectroscopy. If measurement of atomic species is by absorption, then it is called as atomic absorption spectroscopy. And if measurement mode of atomic species is emission, then it is called as emission spectroscopy. Today we have to discuss the atomic emission spectroscopy. And this atomic emission spectroscopy, that is also called as a flame emission spectroscopy. Therefore, here every spectroscopy technique measures two important parameters. First one is called as wavelength. The wavelength of absorption or emission is the identity of the material, and the intensity of radiant power that is absorbed or emitted by the of the atomic species present in the sample, and it is measured through emission mode and is called as atomic emission spectroscopy. Therefore, plain atomic emission spectroscopy is the branch of atomic spectroscopy involves the thermal excitation of gaseous metal atoms and measurement of radiant power, at specific wavelength emitted by the atoms when those are de-excited to ground state. Flame atomic emission spectroscopy is a branch of atomic spectroscopy. It involves the thermal excitation of the gaseous metal atoms and measurement of the radiant power at a specific wavelength emitted by the atoms when those are de-excited to a ground state level. Therefore, this is a definition of a flame atomic emission spectroscopy or flame emission spectroscopy. In flame emission spectroscopy, the wavelength at which the radiant power is emitted by the atomic species is the identity of atomic species is the identity of atomic species. While the intensity of radiant power at that specific wavelength is related with number of atoms. Is related to number of atoms de-excited to ground state level. Therefore, in flame atomic emission spectroscopy or in flame emission spectroscopy, the radiant power emitted by atomic species at a specific wavelength is the wavelength at which the radiant power is emitted is the identity of the material, and the radiant power at that wavelength is proportional to the amount of atoms those are de-excited from a excited state to ground state level. Therefore, here, for example, the characteristic golden yellow color imparted to the flame is the identity of sodium atoms in the flame. Sodium atom in the flame emits wavelength 589 nanometer and which has a golden yellow color. When we aspirate a solution of sodium, that is sodium salt, sodium chloride, sodium bromide, then characteristic golden yellow color imparted to the flame that indicates sodium atom is present in the flame. The wavelength of this golden yellow color is 589 nanometer. Therefore, here this 589 nanometer is the identity of the sodium atom. And if we measure the intensity at 589 nanometer, intensity means radiant power is equal to the amount of sodium atoms in the flame. Therefore, here in flame emission spectroscopy, the wavelength at which substance or that molecule atomic species shows emission is its identity, and intensity or radiant power at that wavelength is related with the amount of material or amount of atoms present in the flame. This is the underlying principle of a flame emission spectroscopy or atomic emission spectroscopy. Student, we know that flame atomic emission spectroscopy is limited to determination of alkali and alkaline earth metals. These metals are easily atomized by using a flame temperature, as well as these atoms are excited by using a thermal energy. Therefore, here the flame emission spectroscopy is limited to determination of alkali and alkaline earth metals. Here we discuss the principle of a flame emission spectroscopy. Suppose, for example, a metallic salt solution, when aspirated into the flame, that mix with fuel gas and the air or oxygen and get converted into MX mist. Mist, that is a fog. That means a sample solution with the fuel gas and oxygen. This mixture results in formation of fog, and that is called as mist. This mist contains that particular metallic salt plus a fuel gas as well as oxygen. When evaporation of solvent takes place, here this MX is converted to MX solid. This MX solid, when undergo a evaporation, then it is converted to AMX gas. This MX gas is further dissociated to M gas plus X gas. That means here gaseous atoms are formed. These are the atoms, not ions. When this solid dissociates, that converts into the gaseous atoms. Here, these gaseous atoms absorbs a thermal energy from the flame and it goes to the excited state. This means here, suppose for example, there is sodium atom. This sodium atom absorbs thermal energy. Then outermost electron of the sodium atom, that is electron present in valence shell, is get promoted to the excited state, and for this purpose this thermal energy is utilized. When that atom gives its electron to next valence shell, then it is said to be in excited state. And this is a state that is called as excited state, and that would be obtained by absorption of energy. It is in the form of heat energy or a thermal energy. This excited state of any matter have very short lifetime, and when it comes back to ground state level, that emits absorbed energy as a h nu. The energy of emission is equal to Hc upon lambda, since mu is equal to C upon lambda. Therefore, here characteristic color is emitted by this particular emission, and that is the identity of material. Therefore, here a lambda is the identity. And when we measure the radiant power of this emission at that specific wavelength, then it is related with the amount of material. That means here, when metallic salt solution aspirated into the flame, that mixed with fuel gas and oxidant or air, resulting formation of mist, that is a fog formation, that is a mixture of solution and gases, from which the solvent is evaporated, then a mx solid is obtained. This solid further converted to a mx gas by vaporization, not evaporation, vaporization. And here, when this vaporized gaseous metallic salt undergo dissociation, it gives a gaseous metal atom and its coatom. This gaseous metal atom undergo a thermal excitation by absorption of thermal energy from the flame, and when it reaches to the excited state, it when come back to ground state level, that means when it again come to this its original form, then it emits a radiation. The wavelength of that radiation is the identity of the material, and radiant power at that wavelength is related with the amount of material. In this way, this flame emission spectroscopy works. After the principle of measurement in flame emission spectroscopy, we discuss the emission spectra and its application in analytical chemistry. Here, consider the sodium atom. Sodium atom, when we aspire it into the flame, sodium atoms are formed. These sodium atoms are converted to sodium gaseous state atoms, and these gaseous state sodium atom undergo thermal excitation, and that emits a radiation. Here we have to discuss how the golden yellow color appears to the flame when we aspirate the sodium atom into the flame. One of that sodium have 11 electron. That means 1s2, 2s2, 2p6 and 3s1. Actually, if we consider the atomic structure of any atom, first cell that consisting of 2 electrons, second cell consisting of 8 electrons, third cell consisting of 18 electrons, and fourth cell consisting of a 32 electron. Therefore, here 1s is the first cell of any atom, or here sodium atom. Therefore, 2p is the second cell of the sodium atom, and here if we have a more electron, then 3p is the valence cell of this sodium atom. Therefore, 3p is the valence cell, because here third cell is 3s cell, but here s is sub level, or 2s, 2p, these are the sub cells or sub levels. Therefore, 3p is the valence cell of the sodium atom. Therefore, here when we aspire sodium into the flame, this outermost electron is present in 3 3s level. That means in a 3p valence cell. Now here this 3p valence cell, then 4p, then 5p and then 6p like this. Here we consider here this is the valence cell 3p, 4p, 5p and 6p. Initially when sodium is in gaseous state and it is in a ground state level, then it is the electron present in this 3p, that is a valence cell, or it is called as a ground state level. This is a ground state level of the gaseous sodium. Therefore, here when this sodium gas atom absorbs thermal energy, then it is given into the excited state. That means what happens? This 3s electron is promoted to 3p level, or this 3p to 4p, 4p to 5p, 5p, and 3p to 4p, 3p to 5p, or 3p to 6p. That means here this electron which is present here is promoted from this first level, suppose E0, to 4p E1, or sometime to E2, or sometime to E3. Here the single electron of single sodium is excited from this ground state level to first excited state level, ground state level to second excited state level, ground state level to third excited state level. Here 3p is a ground state or valence cell or ground state level of gaseous sodium atom, 4p is a first excited state, 5p is second excited state, and 6p is a third excited state of the sodium. Now here this electron is get promoted from ground state level to different energy levels depending upon the absorption of energy. That is the excitation by absorption of energy, absorption of thermal energy, because here no other source is present. When this electron, single electron of single sodium, either promoted from E0 to E1 or from E0 to E2 or from E0 to E3. That means here single electron may given this level or this level or this level. That means here these are the transitions shown by the three different sodium atoms. Single sodium have a single valence electron. It gives only single transition, and that transition will be depends upon the amount of energy available. If less energy is available, this transition can easily occur. If more energy is available, this transition occurs, and if extra more or greater energy, that gives the electronic excitation from E0 to E3. That means here when this situation taking place in the atom, that is valence cell electron is either promoted to first cell, is either promoted to second cell, or is either promoted to third cell, then we can say that there is excitation of atom. Then here this is a first excited state. You may say first electronic excited state. This is the second excited state, and this is the third excited state. First, second and third excited state means electron is promoted from first level, ground state level to first electronic energy level, first excited state electronic energy level, ground state level to second electronic energy level, ground state level to third electronic energy level. This will be possible depending upon the amount of energy available. When molecule undergoes such a type of event, then we can say that that will be excitation by absorption. And here, during the excitation, here this electron is get promoted from this level to this level, or this level to this level, or from this level to this level. That means here electron which is promoted from E0 to E1, that is also excited from E1 to E0. During this excitation, whatever the energy here emitted by the radiation, that is 589 nanometer for the sodium. Similarly here, for this second excitation, the energy is 330 nanometer, and for this third de-excitation, energy is 285 nanometer. Now this is called as emission, and this will be emission taking place when there is de-excitation. De-excitation means a electron is promoted from excited state level to ground state level, and during this it emits absorbed energy, and that is in the form of h nu, whose wavelength is related with the energy gap. In this case, you will observe that highest energy gap we have a wavelength at shorter region. Smallest energy gap we have a wavelength at a longest region. That means here emission will be occurs at longer wavelength when energy gap is small. Emission will be occurs at a shorter wavelength when energy is greater. That means here there is inverse relationship between the emission energy and emission wavelength. In addition to this electron may be promoted, may be de-excited from this level to this level, sometime this level to this level, or this electron may be promoted from this level to this level, or this level to this level. Therefore, in addition to these three different emission lines, sodium also shows some emission line in this fashion. That means when 3p electron de-excited to E2, E3 electron de-excited to E1, or E2 to E0, or E2 to E1. Therefore, here these type of line are also occurs when sodium is de-excited from a excited state to ground state level. Now, in this case, when electron is de-excited from a excited state level to ground state level, that emits energy. This energy is equal to h mu, where h is called as Planck constant, and we know its value 6.626 into 10 raised to minus 34 Joule second, or 6.626 into 10 raised to minus 27 Earth second. Here in this equation, E means this energy gap, that is delta E. Therefore, delta E is equal to h mu, or delta E is equal to hc upon lambda, since mu is equal to c upon lambda. In this case, c is a velocity of light, and its value is equal to 3.0 into 10 raised to 8 meter per second, or 3.0 into 10 raised to 10 centimeter per second. Therefore, here we can write this equation in this form, Sc upon delta E. Therefore, here from this emission spectra, it is clear that the wavelength of emission, that is lambda, is totally depends upon the energy gap between the two levels, that is the excited state level and ground state level. In this case, lambda is inversely proportional to delta E. Here H is constant, C is constant. Therefore, here value of wavelength of emission or emission wavelength is directly related with the energy difference between the excited state and ground state level. Here this delta E is equal to E1 minus E0. That means here energy gap between the two levels, excited state level and ground state level, is the delta E. And this equation is utilized for determination of a wavelength of emission as well as the energy required for excitation. Now here, with this emission spectra, we derive this equation. And here, for sodium atom, we have three prominent emission lines: 589 nanometer, 330 nanometer, 285 nanometer. When electron is de-excited from first level, that is excitation, de-excitation of electron, de-excitation of electron from first excited state to ground state, whatever the energy is emitted, that is called as resonance energy. And it is also called as, this line is also called as resonance line. Resonance line or resonance energy, that is the energy released when a electron is de-excited from first excited state to ground state level. The intensity of this resonance line is more because here this type of transition easily occurs because it requires very small energy. Therefore, many sodium atoms undergo this type of electronic transition because it requires minimum energy. Therefore, here the resonance line, that is the emission line obtained when that atom is de-excited from a first excited state level to ground state level. And this resonance line is generally selected for the qualitative and quantitative analysis. Because here this resonance line have more intensity because probability of this electronic transition is more. And therefore this more intensity line can be easily isolated for identification and estimation of the sample. Therefore, resonance line is utilized for the identification and estimation of the particular atomic species. Therefore, sodium is identified by this wavelength 589 nanometer, and it is estimated by measuring its radiant power at 589 nanometer. This is the basic principle of emission spectroscopy on the basis of emission spectra. Student, based on this discussion, you can find out the answers of the following question. Number one is, what is flame emission spectroscopy? Give its principle. What is emission spectra? What is emission spectra? How does it obtain? Explain its analytical importance. And next question, that is number 4. What is resonance line? With our today's discussion, you can find out the answers of this question. With this discussion, we stop here. Thanks for joining me. Keep learning. Happy learning.